Okay, so for the just an announcement about the final exam. The exam will be released on grade scope as per the university schedule. I forget the exact date, but it should be on the calendar, on the course website, and I'll release it within a 24-hour window. I know that people are in different time zones. In the 24-hour window, you can start it at any time that you want, but once you start it, you have to finish within 3 hours. Okay, it's kind of a timed exam, but you can pick the window of time that you want to work on. All right, and any questions about it? And it will cover all the material that we've seen in the lectures, and working through the homeworks, trying to understand what they were doing. I think that would be the best bet towards preparing for the exam. Okay, any specific questions about the final? And it will have essay problems and some sort of objective questions which you'll upload answers on Gradescope. I don't want to give a longer window because I'm sure you have many other exams, so I think don't want things to be overcrowded for you. Okay. Alright, so let's get back to what we were discussing last class. So we introduced this really important class of probability distributions called graphical models, right? And we saw some examples of them, and we asked the question of when can we learn graphical models. And the question by the first one we started out with was ill-defined, and then we started specializing it. So this led to the important notion of T-wise Markov random fields. Okay. And today what we'll do is to give an algorithm which in full detail, which learns a special class of Markov random fields which are known in machine learning literature as Boltzmann machines. Maybe you've heard that term in the context of neural networks or restricted Boltzmann machines or RBMs and things like that. And we'll see an algorithm for learning them. Okay. And I should say that although we are working with Markov random fields when we see the entire distribution, one of their most important things is the case where some variables are hidden, and I'll touch upon that towards the very end. Okay. So let's recall. Said distribution D on I have a distribution D which is on D variables, little d variables, is a T-wise Markov random field if the probability density function can be factored. It's called a factorization because you're writing it as a product of things. Pi C a clique or S in G, size of S is at most T, and what was the letter that I used in last class? Score. Okay, so this is what the probability density function looks like. And you might wonder, what is this proportionality sign here, right? So we are not writing an equation for the probability density function. I'm just telling you that is proportional to something. Okay. So there, when you think about it this way, there are many questions that show up. For example, even if I tell you the scores, can I sample from the distribution efficiently? Right? So there's just so much research in this area that I can't touch on all the questions. So we are studying learning MRFs. Okay, and there's a parallel field where you just want to sample from MRFs. And there's a lot of work in theoretical physics practical/statistical physics on this. And information theory. And in machine learning. So somehow, all three of these, and also of course, in theoretical computer science. So Markov random fields show up in all of these areas. In information theory, people study what are known as belief propagation algorithms and try to understand what they do for sampling. Statistical physics people try to understand phase transitions and things like that. Machine learning people, we use optimization techniques. Can I do some kind of gradient descent? That's our hammer. So to try and sample. And TCS, you design algorithms and the cases to study them. Okay, so this is after knowing the Markov random, right? So what we are asking is, can I even learn the Markov random field? Okay. All right. So just to get some intuition, and I think it's a very important case by itself, we'll study what are known as Boltzmann machines in the machine learning literature. And they are known as Ising models in physics literature. Okay. So this is basically a t-wise Markov random field where you take t to be 2. Right. So this is just equivalent to 2-wise Markov random field. And just for concreteness, right, and pretty much any case can be reduced to this binary case. Let's also consider the situation where the domain of the distribution is just bits. Okay. You can generalize it to larger alphabet. Once you make it continuous, it's a completely different story, and we'll talk about that in the next lecture. But as long as it's discrete, you can make it, kind of reduce it to the binary case. So let's focus on the binary case. So what is this? There is a graph G, which is the dependency graph. Putting quotes on the wrong place. And what does it mean to say it's a 2-wise Markov random field? Right, so let's go back to the formula. So here we're saying you're taking cliques in your graph of size at most t. Right? And if t is 2, what are cliques of size 2 in your graph?
Edges.
Edges. Right? So it's just saying that you have your graph, let's say it's something like this. 1, 2, 3, 4, 5. Then your probability is proportional to functions on the edges, that's all. Right? So for each edge in the graph, an edge, you look at some score function e of xi, xj. Okay. So somehow you have functions on pairwise, variables, and then you're multiplying them. Okay. So when studying graphical models, it's often convenient to not talk about score functions and like taking product of score functions, but it's nicer, for reasons coming from physics actually originally, to write things as sum. Okay. So what do I mean? So let's think of writing the score function as some e to the some say L score. Okay, so I'm defining L score is basically the log of the score function, right? It's just another function. And if I parameterize it this way, then what I get is a product. Okay, and the nice thing is it becomes sum. Okay, so I mean I haven't changed anything meaningful here. I just changed the way I'm parameterizing the score function so that the thing looks like, you know, e to the some sum instead of taking products of things. Okay, and remember that xi and xj were bits, right? So what do I have in this exponent here? Can I write it in a more succinct way? So think of basically what's the degree of this function if I think of it as, you know, a polynomial in x1 through xd. What's the degree of that function going to be at most?
2.
2, right? Basically I can write any function on two variables as a degree to polynomial. Right? So basically this means that I can write it equivalently as so I'll get some linear term and then a constant term. Okay, and this is the form that people write Boltzmann machines usually in. You know, whenever you see Boltzmann machines or Ising model in the literature, you'll see it in this form. Okay, and the name Boltzmann itself should tell you something, that it comes from physics. You know, Boltzmann was a physicist who studied phase transitions and things like that, and it has its origins there. Okay, and the way to think about this Aij coefficients is basically you have a weight on each edge, right? So you have something like this, and 1, 2, 3, 4, 5, and you have some numbers sitting on the edges. Okay, so let's say, you know, the numbers are 1, 0.1, 0.1, 0.1, 2, 1. Then it's saying probability, example, x equals x is proportional to, we'll often ignore the linear term. The linear term is not so important because we are really interested in learning the graph structure. And the graph structure is coming from this pairwise interactions. Okay, is e to the, like, you know, in this case it would be x1 x2 plus 0.1 times x2 x3 plus x3 x4 plus x2 x4 plus okay. And the reason they show up in physics is basically, by the laws of thermodynamics, when you try and do, like, if you think of this as some kind of charged particles which are interacting on some graph structure, then the least energy configuration corresponds to something like this, and that's where they come up from. Okay. All right. So now what are we saying, right? So our problem, what is the computational problem that we are asking? Right? So we are asking, I'm giving you samples, X from samples x1, x2 up to xn on 1 minus 1 to the t from an Ising model. Okay, and our goal is learn the graph G. Okay, and the assumption is that the graph is somewhat sparse. So let's say G is sparse, meaning each vertex has degree less than or equal to k. So how can I find this underlying graph given samples from this distribution? Okay. Any questions about the problem? All right, so before going there, let me say a couple of things about why they are so important. One is there's this thing called restricted Boltzmann machines. So what's a restricted Boltzmann machine? It's essentially a Boltzmann machine where the graph is bipartite. Meaning the edges, there's like a set of variables x, there's a set of variables, let's say x1, x0, okay? And the edges are only going from the top layer to the bottom layer. There are no edges within the top layer. And you believe that basically the joint distribution of these things is coming from a Boltzmann machine or like the Ising model with these rates. So Bm with G being bipartite. Does this ring a bell anywhere? Has anyone seen something like this in some other context?
Can't bipartite graphs be used for like hypergraphs, almost like hyperedges?
Right. So basically, what happened in the these were studied for a long time in machine learning and statistical physics and so on, and then in kind of in mid 2000s, Jeff Hinton and others realized that you can use this to train neural networks. So what they did was suppose that you can stack these Boltzmann machines one on top of the other. Now suppose I have multiple layers like this, and I assume that somehow any two consecutive layers, their distribution is like a Boltzmann machine. Okay, and they use this and some heuristics to train their first neural networks, and that led to breakthroughs in image recognition. So what was the problem that they were studying, right? So they said learning RBMs with hidden partition. they said, suppose I'm actually getting samples from just a 2-layer, like, that's a real RPM, just 2 layers, okay? But you only see X1. Okay, think of it as some kind of neural network, and they said, okay, forget, I only see the outputs of the top layer. Can I still learn the network? Can I still learn the underlying graph just from seeing one side of the observations, whereas the other side is hidden? And what they did was, okay, I can do some kind of gradient descent to try and learn the network using this. And then I'll just do it repeatedly for each layer by layer training, and magically it led to really good performance for neural networks. This was at the beginning. Now we have lots of ways to go around it, but it's good to know that somehow these RBMs, and especially this problem of RBMs with hidden partition, was at the core of the early empirical progress in neural networks. And what we're going to see is, okay, if you really want to solve the problem with hidden nodes, let's solve the case where you even see both sides. Can you even do that? Okay, and we'll see that we can do that, and this problem is still wide open. I mean, you can do some heuristics, but we lack any understanding of when this problem is efficiently solvable. There are some hardness results which came out, I think, a year or two ago, but there should be very nice ways to go around it, and that's a major open problem in machine learning and in the theory of deep neural networks, whether we can learn restricted Boltzmann machines with hidden partition under some reasonable conditions on the graph. Like if the graph is sparse, the weights are random maybe, can you still do it? We don't know. Okay? Alright, so that's a bit of the history. And let's go back to our question, which is to learn this Ising model. And one more thing I want to say is, so before I say that, so what is the best possible scenario? Okay. So what is even possible? Right? Meaning, so there are many parameters here, right? So how many samples are needed? As a function of the dimension d, the degree k, and epsilon the accuracy. Okay, and next is what is the runtime? How many samples we need? Like even if I allow you infinite computational power, what is the best you can do in terms of number of samples? Okay. So here we need to make, so let's see, so basically we have a good answer to this question, which is kind of actually surprising. So let's recall the representation of the Boltzmann machine, right? So it was actually you can ignore this guy because it's just a proportionality thing. Okay, so this is what we have, right? So one thing is, if I have an edge in my graph, but the weight is really small, then it's going to take me a long time to identify that edge, right? Even if there's just a single edge and the weight is really small, it's going to take me a long time. Okay. And the other thing is that, the contrapositive of that is that if the weight of one wedge is much bigger than everything else, then you're going to need a lot of samples to see the gap between them. So we need some normalization on the weights. Okay. So let's say that each weight Aij is, in some interval alpha comma beta. You think of these as like maybe 0.01 and this is maybe 10. These are just weights on the edges. You can think of these numbers which are coming from some range like 0.01 to 10 to something like that. These are reasonable numbers. We don't want the complexity in terms of these numbers. We're really interested in the complex in terms of the dimension and the degree. Okay? And the same for AI. So in terms of statistics, how many samples are needed? Santanam and Wainwright, these are two statisticians and ML researchers, in 2008 showed that you need basically 2 to the O of k times log d samples necessary and sufficient. Okay. If you think of these alphas and betas as constant, they showed that you can get by with only logarithmic in the dimension many samples. You have exponential dependence on the degree, but that's okay. That we are thinking of the degree as being something very small. Imagine you have your data is like genome sequences, right? So the dimension is 1 billion features and the degree is maybe 5 or 10. So then the gap between log d and d is humongous. Okay. So it's saying you only need logarithmically many samples to recover the graph, which is very remarkable, right? Because somehow you're learning information about the entire graph, but only from logarithmic many samples. And this is for the entire graph, not just like small neighborhood thing, the whole graph.
Why is like degree very small like a realistic assumption?
Right. So basically, the two reasons. One is if it's not small, this is not the right model. Okay. The other thing is, often when you apply these things, like let's say you think of, these are all explanations that you hear from practitioners, right? Like let's say your data is basically genome sequencing. Then you have some correlations, but it's not exactly like a Markov chain. If it were a Markov chain, the degree would have been 2. Right? But maybe along with that basic Markov chain level kind of thing, you have some edges which jump back or forward. Right? So you have the base skeleton and then you have a few edges. So once again, the degree is small, but those jumps are important. Okay. So that's basically one reason why this is an appealing assumption practice. All right. So logarithmic can d many samples. That's all we're going to get, and we have to identify the entire graph using that. So this result is remarkable, but it only showed that it is possible to do it. It didn't give an efficient algorithm to do it. Like, it essentially said that if you have a lot of computational time and power, you can do it. Basically, it needs runtime, which is like d to the k, kind of like enumerating all possible graphs, which is like d to the k. So it's kind of not very feasible in practice. Okay. So that's how things were, and in I think in 2014 or 2015, Guy Bressler, he showed that gave a O of n times d squared runtime algorithm. With n being 2 to the 2 to the O of d by epsilon time. Oh, okay, sorry. Doubly exponential in d is definitely not interesting. Okay, so designing an efficient algorithm for this for Ising models or Boltzmann machines was kind of open for a long time, and then Bressler showed that he gave a quadratic time algorithm. So it's great, right? So you just have to kind of run in time, which is d squared, and get something. The number of samples is still logarithmic in d. Okay, which is kind of what we were expecting from the statistical results. All right. And what we're going to do in this course, in this lecture, and maybe at the beginning of the next lecture, is to give a different algorithm. And this is due to Clymon's with, this is my joint work with Adam Clymon's from 2017. We gave again O of n times d squared runtime algorithm with the number of samples is basically 2 to the O of k, sorry. Okay, so it's kind of, optimal statistically. It takes the optimal number of samples, and the runtime is quadratic, and outputs the Ising model. And something that we won't cover here is that actually also works for t-wise Markov-random fields. So I only stated everything for 2-wise Markov-random fields or Boltzmann machines, but the algorithm that we are going to cover can actually also be extended to 3-wise Markov-random fields, or more generally for t-wise Markov-random fields. It'll take a hit in the runtime, but it'll still be better than just brute force d to the k runtime. Okay? So when we come back, we'll study how to get this algorithm. And when I say we'll get this algorithm, you actually already seen the algorithm. You actually already coded the algorithm. You just have to kind of apply it suitably for this problem, as we'll see. Okay? Let's take a 5-minute break, and when we come back at 10:40, we'll start thinking about how to learn Boltzmann machines. All right, so here's the question. You're getting samples from this distribution X, which satisfies this condition, and we want to figure out what these weights are. I mean, it seems very complicated, right? Like, how do you even start approaching this question? And magically, there is one lever which will crank it up, and that will help us solve the problem. And that lever is also kind of very important when you go back to this connection to neural networks. So what is that lever? So it's a property of these distributions, which is why actually, it's one of the reasons why they keep showing up in practice. What is that property, right? So imagine, I'm trying to have these d features. Let me try to single out this one guy, xt. Okay, so imagine, I have my graph, I'm putting this one feature xd aside, and I'm trying to figure out how this dth vertex interacts with everything else before. Okay, so what can I do to address that? Like, how does the behavior, how do these variables 1 through d minus 1 influence the distribution of xd? Okay, so how do they do it? Well, so what's the way to ask that question? What would you like to know if I ask you, okay, here's a qualitative question. How does an assignment to x1 through xd minus 1 influence xd? What's a quantitative form of that?
What's the probability x equals xd given x1 to xd minus 1?
Exactly, right? Let's say I'm interested in the conditional probability distribution, conditional distribution of xd given everything else. I have d features. I'm trying to understand, my whole goal is to study how one feature is affected or depends on the others conditionally. So, I give you everything but one feature. What can you tell me about this feature? Right, so let me write it this way. So this is notation shorthand for x minus t means omit dth coordinate. Okay. So this is my question, and how can I answer this? Well, we have our formula, right? So let's see what happens. So I'm interested in probability xt equals 1 and x minus d equals x minus d. Okay? So let me first write down this. The AND question of the two, right? So if I put an AND here, let's say, let me write it better, and x minus e equals x minus d. We know it's proportional to a bunch of things, something, and I can also write the same thing for if I knew these two, how can I get the conditional distribution? Let me call this number, maybe P1. This is, let's say, P minus 1. If I know these two numbers, how can I get the conditional distribution? Looks like a Bayes rule. Yes, Bayes rule. Okay. So Derek, did you have a question? I just saw your comment. Looks like a fully connected network.
No. Oh no, that's the where I go.
Okay. All right. So basically, we can use Bayes rule, right? And can you tell me what does P1 depend on? It depends on something, right? It's a function of something. What is it a function of? It's a function of minus d, right? All but this partial assignment. It's some number. I don't care what its number is, but I can use Bayes rule. So what does Bayes rule tell me? Okay, this is what Bayes' rule tells me, right? It's a probability, because these are the only two events I'm interested in, xt equals 1, xt equals minus 1. So it only depends on these two numbers. The other numbers, I don't care. The other points in the probability space, I don't care. It only depends on these two numbers, the relative ratio between these two, really. Right? So I can write it even more succinctly as, let's say, 1 divided by 1 plus just kind of the ratio between these two numbers, right? What's the ratio of minus 1, the probability that x equals minus 1 and the rest are the exact partial assignment, and x equals 1 and the exact partial assignment. Alright, but now there's some magic that's happening, right? So what is this ratio? What can you tell me about this ratio? I'm claiming that it simplifies a lot. But what's the first simplification? We have a proportionality symbol here, right? So when I take the ratio, what would I get?
It's just the division of those exponent functions.
Exactly, right? Because the proportionality constant will disappear. I mean, that's the whole advantage of looking at conditional probability. You don't have to worry about the normalization. Okay? So it's just going to be exponential of summation I comma j. I need to write it properly, so let's see. These are, let's say, in d minus 1, I get xi xj, right? But xd is being set to be minus 1, right? So I get plus j equals 1 through d minus 1 of a dj minus 1 xj. Okay, and then I have the linear terms. Okay, I'm separating this sum as indices that are coming from 1 through d minus 1 and the dth index, and I get this expression. Right? Any questions? And I get the same thing in the denominator. Okay, so let me do something here. So the only changes are these guys. Okay, so between these two probability, whatever I'm plugging in there, the only thing that's changing is the assignment to the dth coordinate, right? So if I go back to the expression for the formula, only those things which involve the dth variable will survive when I take the ratio. Okay, so what happens when I take the ratio here? I get a lot of nice cancellations, right? But this and this goes away, right? And this and this goes away. So what am I left with? I get p minus 1 of x minus d is So the ratio became a linear exponential in a linear function. Okay. So let me write it more succinctly. I'm going to write this as x of some w star. No, actually, let me just say w comma x minus b minus okay, so I'm abstracting the question. So it's just saying that the ratio is exponential of a linear function on this x minus d. All right. So now if you go back to our this ratio, what do I get? So by the base rule, is actually 1 divided by 1 plus okay. And what is this guy? What is this function? 1 by 1 plus e to the z.
Isn't this using logistic regression?
Exactly, right? So it's a sigmoid function. So at the end of the day, we went through this very circuitous route, but what you end up with is something which looks really like logistic regression, right? Is sigmoid of actually I think sigmoid is defined with minus z. So okay, sorry, let me make one change. Okay, and remember that sigmoid was this function with z is 1 by 1 plus e to the minus z. Okay, and the way it looks is okay, it's basically saying the conditional distribution of one node given everything else is the sigmoid. Okay, it's kind of almost like a linear regression type question now, right? Except that you have a sigmoid sitting there and there is some noise. Okay. And the point is that if somehow here W exactly captures the coefficients of the matrix, right? So Wj was minus 2 times ADJ, and theta was exactly minus 2 AD. So intuitively, what I can maybe it's a little too optimistic. But let me forget completely about the Ising model and everything. The fact that all of the variables have relations between them. And let me zone in only on the dth vertex and trying to infer its neighborhood. What are the coefficients associated with this vertex? And I'm just going to focus on solving this problem now. I give you samples where the one variable, the conditional distribution is a sigmoid. Can I infer the unknown linear coefficient? which is exactly logistic regression, right? And if you are wondering why, why these Boltzmann machines showed up in the early works and neural networks, this is one of the reasons, right? Basically, if I think of a neural network where my activation functions, I have some input, right? And then my activation functions are sigmoids. Okay? But if I have noise after each layer, imagine, I don't output the sigmoid exactly, but I discretize it in each layer, right? Then what you're getting is a sequence of Boltzmann machines stacked on top of one another. Okay, so that's one of the reasons why they showed up in this early works on training deep neural networks. All right, does it make sense? Any questions about this? So in some sense, we are reduce the entire problem, not reduce, but at least hoping that solving the following would suffice, and let's try and solve it. So what does it suffice? So it suffices to solve the following. And what is the following? So let me call, I'm going to change notation a little bit to make it more clear as to what we're doing, right? So this xd, all but the first coordinate, all but the last coordinate, sorry, I'm going to call it a new variable. So let's say x bar is x1, x2, up to, these should be uppercase letters. Okay, and y bar is just xd. Okay, and now I'm phrasing it as the logistic regression problem essentially, right? So input is samples n samples where these are all in 1 minus 1 to the d. The conditional distribution is exactly sigmoid of some w star comma x plus theta. And the goal, so what should our goal be? Any guesses? What should the goal be?
Produce W, which is close to W star.
Yes. So ideally, we'd like to say that, produce W which is close to W star, because that would solve our problem. But in this generality, when I don't assume anything about x bar, it's not going to be possible always. Right? So, here in this formulation, I'm trying to forget everything, all the additional information I have about x bar. That it itself is coming from some kind of, Ising model. Right? But I'm just trying to set it up as a regression problem. And in regression, usually, it's, you don't ask for getting the unknown coefficient vector exactly. It is possible in some cases, and in those cases, you shoot for it. But otherwise, you just shoot for small prediction error, right? So I would like to find a W which kind of approximates y bar, gives me good guarantee in approximating y bar. Okay, so output W such that you minimize some kind of loss function. And the loss function, you can take all kinds of loss functions. One of the most natural ones is to take the squared laws. Oops. Let me write it down here. Okay, that's the problem now. We went from graphical models, Ising models, to solving this sort of almost plain vanilla linear regression question. All right. And these sort of models, if you're interested in looking up this further, these sort of assumptions where I place an assumption on the conditional distribution of the regressing variable, right? So y is the regressing variable, x are the covariates. This is called the probabilistic concept model. Basically, the only assumption I'm saying is the conditional mean is coming from some class that I know, which is just like the sigmoid of this linear function. And the choice of the loss function, here I'm using squared laws because it kind of works easier for us, but you can also work with the usual logistic laws, all kinds of other losses too. Okay? And there's also a name for it. So we mark you can ask this for other activation functions. So by activation function, I mean the sigma that you're applying. So what you're doing is you're working in some d dimensions. You apply a linear function on that, you get a number, and then you send it through the sigmoid gate, right? Which is what happens in all kinds of neural networks, right? But there are lots of other activation functions that people look at, like for example, ReLUs. Sometimes people look at power activation functions, tanh activation functions, all kinds of things like that. So for all of those things, you can ask the same question. What if my conditional mean is, some activation function of a linear function? Can I learn the linear function? Can I get small prediction error like that? And in this general framework, it's called generalized linear models, or GLMs. And these we briefly touched upon when we were kind of testing out gradient descent. Okay? You can also think of it as the problem of learning sort of a single node neural network with some activation function where you have noise. Without noise, thing is easy, but with noise, because somehow y bar is not exactly equal to the sigma, but it's only equal to it in expectation. Okay, any questions about this general problem now? These GLMs themselves have a history of their own, right? You have the graphical models, Ising models, they have their own history, and now here on a parallel track, people were studying GLMs, and we're just kind of connecting these two things together now. All right? Okay. So what is known about GLMs, right? So given that linear regression is so old and logistic regression is so old, you'd imagine that GLMs are also extremely well studied and we know everything there is to know about them, right? But surprisingly, they were not that well understood. And the most relevant result for us is due to Kakade, Kalai, Karande, and Shamir from 2010. I mean, on the scale of linear regression, which is ancient, this is pretty modern, right? Just 10 years ago. What they showed is that can solve with n is O of d by epsilon squared samples. Okay, so recall whereas Wj are okay, so we had an assumption that the weights of this unknown W star are bounded, right? They're exactly this minus 2 ADJ, and there were some constants between minus 0.001 and minus 10 or something like that, so they're bounded. Okay, and they showed that you can do it with something like d over epsilon squared samples. So is this good for us? What do you think?
Probably not.
Yes, why? Because we have this linear and d dependence, right? But in our case, we don't have that luxury. We have a tiny amount of data, a tiny number of samples, logarithmic and d many samples. So how do I get around that? Okay, so how do we get around that? Well, it's not a mistake of, it's not really a shortcoming of this work, because they're not exploiting something that we know about our specific instance of the generalized linear model. Something that we have additional knowledge of and we should exploit. And what is that? So is the W star in our case any d-dimensional vector, or do we know something about it?
Well, each entry is bounded.
We know each entry is bounded, but that's also assumed by this triple KS. What else? Well, think of what are these coefficients, right? These are this minus 2 ADJ. So it depends on the graph. And what do we know about the graph? So basically the coefficients here correspond to the coefficients of the dth vertex. Right? So we have, all of these guys, these are d minus 1, and then I have d. And d has some edges. Okay? How many edges does it have?
At most k.
At most k. So how many non-zero entries can W star have?
K.
K. And we're thinking of k as a constant, small number, right? So what is really missing here is that it's not exploiting the fact that W star is sparse. Okay? So, idea. Need to exploit that W star is k sparse, i.e. has only k non-zero entries. Okay, and in some sense now we are asking, I have a generalized linear model, but the coefficient vector is sparse. Can I exploit this sparsity to get convergence in much fewer number of samples? Okay? If I tell you there are only 10 non-zero entries, how many samples do I need to get epsilon accuracy? All right. Can we exploit their sparsity? I mean, if I can do that, that would be a meaningful question, kind of a meaningful result, even outside of the specific application we have in mind. Because sparse linear regression problems show up in many, many places. And this is kind of a much stronger generalization of it, where you're allowed to put any activation function. Okay? All right, so, and that's exactly what we are going to do. So actually this paper, KKKS, they started this trend, followed up on this trend. They call their algorithm GLM-tron. You know, if you, this tron is not coming from some tron legacy or like, you know, transformers like Megatron, but it's really coming from perceptron. Their algorithm was kind of inspired by perceptron, so they called it GLM-tron. Okay? And what we showed in this 2010 paper was that we can find, let me say it, there is a linear time algorithm to get error epsilon with n equals O of k times log d to the 4 samples. Okay. So we are saying that you can really exploit sparsity and get convergence, or like, you know, get not convergence, but get prediction error epsilon with only logarithmic many samples. Okay. Does it make sense? Okay. And actually, I want to. So the algorithm, actually, it's not k. It's, I think, k squared. Sorry. Yeah, k squared. Okay. So I mean, it's k squared and not k, but the dependence on d is only logarithmic. Okay, that's kind of great. And we call this algorithm sparsitron, you know, kind of inspired by the earlier works. And this is an algorithm that you already saw. I'll touch on that in a bit. Okay? But is the result clear? We're saying that if I know that W star is k sparse and the entries are bounded, then I can get epsilon accuracy with only k squared log d samples. So now, when this seems somehow too good to be true, right? Why is that? What's the dependence on k here? It's k squared, it's polynomial in k, right? But if you go back a long time ago, somewhere where the way we ended up here was to study this question of learning the Ising model or Boltzmann machine, right? But there, somehow the dependence was 2 to the O of k. So what's happening? What do you think? So why is there such a discrepancy? what could be, somehow, are we done? So we'll see how to solve this in a little bit, but let's touch back and see, does this solve our problem of learning Boltzmann machines? If so, why? And if not, what do we need to do additionally?
Well, we only did this with.
A long time ago, when we were talking about Boltzmann machines, we ended up with this question, right? So somehow the idea was that we had this x equals x is proportional to something. Okay, and then we said, okay, I can write this as a regression problem because so this was our connection to GLM, okay? And to solve if I want to identify the graph, right? What do I know about the AIJs? I know that the AIJs are numbers between like alpha and beta, right? Some numbers, they're just between some 0.001 and up to 10. Okay, and there are k-spars, meaning each row or column has at most k non-zero entries. That's all I have. Okay, and to recover the graph, I need to know each coefficient which is non-zero, right? But what is this parsitron guarantee telling us? It's telling us something in L2 error. Okay, so to get error epsilon, so meaning can find W such that right, so this is what the prediction error guarantee is telling us. But if I want to recover the graph, I need to know what the W stars are. I need to know which are the non-zero coefficients in W star. Right, so I have a guarantee here which is like prediction error. But to solve the original problem, the problem of Boltzmann machines, we need to do what Hadley was suggesting at the beginning, right? Which is I need to find what the unknown W star is. Okay, does it make sense? Like, somehow if I just know that I have small prediction error, I can't immediately say that you also know what the coefficients are. And in fact, it should not be possible, right? We have an information theoretic lower bound that you need 2 to the k samples. You cannot get by with something like k squared samples. Okay, right? Does it make sense? Okay, so here's where the second part of our work comes in. So here's this like a structural result. So what could go wrong here? So what could go wrong, right? Maybe I'm getting small L2 error, but my coefficients are not close, right? And in your experiments, you saw something like this happening on regression problems, right? I forget which homework. I think in the last one or the one before that, you saw something like that happening, right? The L2 errors were close, but one algorithm was giving you much better guarantee in terms of convergence to the true coefficients, right? So something like that could be happening. So often in such cases, you have to show like an inversion result, that if your prediction error is small, that means you are also close in terms of the weights. Okay? And I mean, if you know neural networks, for example, the function 0, right, is can be written as all kinds of neural networks with arbitrary weights. It doesn't have to be just a dumb neural network. You can come up with all kinds of weighted neural networks which output the function 0. So there is no inversion result there. Different neural networks give the same function. So just getting small prediction error doesn't mean you're actually getting the coefficients right. But fortunately for us, we can use lots of additional properties of Boltzmann machines. This part is actually much more tricky than what we're going to do, and I'm going to skip it and show that if X is coming from a Boltzmann machine, then if I tell you that you have small prediction error, so we actually showed an inversion result. These are usually pretty hard to come by. I mean, hard to come by in the sense that they're not true for many models. But for Boltzmann machines, it is true that if you have small prediction error, then you're actually close in the coefficients. But you lose something. If you have epsilon close, then you're only 2 to the k times epsilon close in the coefficients. And the 2 to the k showed up. Luckily, it doesn't, I mean, at least we are, we're not violating immediately getting a contradiction to this old lower bound, right? Which said you cannot do better than 2 to the k. Okay? So it kind of immediately shows up here. So with this inversion result and sparsitron, you are now set to solve the Boltzmann machine problem, right? Basically, what would you do? So full algorithm for learning Boltzmann machines. So what should the algorithm be? I want to learn the whole graph. I have these two ingredients. I have sparsitron, which can give me a GLN style guarantee with sample complexity, which is O of k squared times log t over epsilon squared. And then I have this inversion result, which tells me that if I have epsilon close, my coefficients are 2 to the k times epsilon close. So to close the loop, what should I do? Any suggestions? So what we did so far kind of tells me, I can use it to learn the neighborhood of the single vertex D, right? So what can I do? For I equals 1 through D, hold I out and solve GLM for predicting xi from x minus I using sparsitron. Okay. So if we hold one coordinate out and try to regress it from everything else, and how many samples do I need for this? So with target error 2 to the minus O of k, let's say 2 to the minus k times some epsilon. Okay? And use the recovered coefficients to find Aij. Right? So basically, if I found some vector here, Wi in my regression, then I'm going to set Aij to be, I think, minus half of this. Right? So when we did the regression, sparse regression, the condition was that these W stars are 2 times the corresponding coefficient. And so once I find them, I just scale them up and I get Aij. Okay? And you're basically finding a weight matrix where each entry is close to the unknown entry within epsilon. That's your recovery guarantee. So you're not exactly not just finding the support of the graph, you're even finding the coefficients. Right? So for every ij, I'm finding something which is epsilon close to it. Okay, one last question. How many samples is this algorithm requiring as stated? What do you think? How many samples?
D times 2 to the O of k something. But I guess can you do something where like you share the sample?
Yeah, so if I state it this way, yeah, exactly, right? So somehow if I state it this way, it seems kind of dumb because I'm still needing these many samples, right? Because I'm running these DE loops. But you don't have to do them independently. You can use the same samples to run everything. For I equals 1 to D, hold I out. So let me say, actually,
You just make all the samples before the loop.
right. So basically just run all in parallel on the same set of samples. Okay. So I mean, you can even parallelize the whole algorithm, right? Each vertex is kind of trying to figure out its own neighborhood using the same set of logarithmically many samples. Okay, and then if I do it, I just get this 2 to the O of k times log d by epsilon to the 4. All right. And the final algorithm, I've stated it in this way of reducing it to the sparsitron, right? You're applying sparsitron to try and solve this GLM prediction problem with sparsity constraint. and then we're just doing it in parallel for every vertex. Okay. So the overall runtime is going to be quadratic because each sparsitron is linear and running kind of d copies in parallel for each vertex. Okay. So overall runtime okay, so it's quadratic. Any questions about this? So in the next class, when we come back, we will solve this sparsitron question, right? It's a kind of a standalone question. We can forget everything about graphical models, solve it, and then plug it back in. All right. And you might wonder if this quadratic is the best possible. If I think of genome-wide scale, genome scale applications, then quadratic is really bad too. I mean, it's definitely better than d to the k, but even quadratic is bad. So what can you do to improve it? We really don't know. Anything better than quadratic would be amazing.
So the quadratic you're referring to is the d squared.
D squared, yeah, d squared. The dependence on the dimension, the runtime is d squared.
Yes. And wait, did we talk about the algorithm?
No.
No,
I'm
we
going
didn't
to talk about it in the next lecture.
Okay, I got it.
Right, the sparsitron is linear time. I haven't told you what it is, but if I just use it, I have to use it d times, so I end up with quadratic.
Oh, I see. Okay.
I mean, quadratic seems somewhat meaningful, right? I have this huge matrix, right? It's a d by d matrix of coefficients, right? So you might think that just to write down the matrix, it takes d squared time, and then I'm kind of running in that much time. But the catch is that the matrix is sparse. It has only few non-zero entries, so presumably you can do it faster, but we don't know. Okay, so let me say that there's one special case where we do know how to do better than d squared. This is really a great result actually due to Greg Valiant. I think in 2012 maybe, saying that if G is a single edge, the entire graph has a single edge. All the variables are independent except two that are somewhat correlated. Okay? What do you think is the best runtime there? If I ask you to find the single correlation, what can you do? I mean, if it's a single correlation, it's kind of easy, right? I just enumerate over all possible pairs, look at which are correlated. That gives me an answer, right? No. But he showed that if G is a single edge, can solve n of d to the 1.72. It's a single edge. The most straightforward way is just go through every pair, check if they're correlated, and then stop. But checking all pairs takes you d squared time. But he found a way to gain something over quadratic runtime. He showed that you can do it in this d to the 1.72 time. The number of samples is again logarithmic, but the runtime is d to the 1.72. And we don't know how to do it if I have, like, let's say, 2 edges or 3 edges or things like that. You can probably hack it out if you have a few edges, but for general graphs, we have no clue as to how to beat this d squared runtime. Okay? But anyway, that's another great question that shows up in all places. If you're curious, this d to the 1.72 uses all kinds of algebraic tricks and uses matrix, fast matrix multiplication and stuff like that. Alright, so in the next lecture, when we come back, we'll solve this parsitron problem. And as I said, you already solved it. We just had to copy paste from something that we did before, and we'll be done with it. And then we'll go on to other graphical models, and this time to continuous graphical models, which are a world by itself. Okay? Alright, I'll see you all on Monday, and bye.
Thanks.
Thanks.